In this video, we're going to 3D scan some motorcycle parts and figure out what kinds of things will scan just fine and what won't, so stay tuned. Hey everyone, this is Matt with Learn Everything About Design, and in this video, we're going to be using this Einscan Pro HD and a turntable to scan a couple motorcycle parts. Now, we're going to cover a lot of topics in this video. We're going to go through the Xscan process, talking about setting up and running these scans, talking about processing the mesh, and overall looking at the end result of our work. We're also going to talk about or discuss surface finish and prep on parts before scanning, and the elephant in the room, whether or not we even need to scan these parts at all. So if you are using an Einscan Pro HD or really any scanner and a turntable, or just you want to look at the general process of how this works, make sure that you do stay tuned. We're going to be breaking this up into a couple of different areas. This video will not include the reverse engineering part in CAD. We can do that in another video. We're going to focus solely on the scanning process. So to get started, the first thing that we need to talk about is going to be the scanner itself. Now, I've mentioned in previous video where I've used the scanner that Shinning 3D did send this to me to play around with for a few months. They did not coach me on what to say. They just simply sent the scanner, sent the turntable, and they asked me to use it, make some videos, and all I have to do for them is do a webinar where I have a live Q&A session. Now, it hasn't been announced yet. When it is, I'll put a post on this YouTube channel if anybody wants to chime in and ask questions. Of course, you can always ask questions in the comments, and my email's at the end of every video, so you can always reach out or join the Discord channel for this YouTube channel. So with that out of the way, knowing that the scanner is on loan to me, it's not mine, everything that you see in this video is my own workflow, it's my own point of view, my own perspective. I don't have any obligation to give them a glowing recommendation or review of the scanner. Having said that, I do think that Shinning 3D has a lot of different scanners across the board. They have this Pro HD, there's an HX series, it goes all the way down to the newest Einstar, which is the handheld hobby or consumer grade scanner. That comes in at around $1,000 US, and there are mixed reviews on it. Most of them are pretty good, but I think a lot of people are sort of somewhere in between that scanner and something like this Pro HD. So we're going to talk a little bit about this specific scanner, the settings that we're going to be using, but I do think it's important to note that there are different kinds of scanners on the market that will do different things. This scanner is going to be similar, with the only variation being things like the amount of points or data it can bring in, the speed, the accuracy, but the structure of the scanner itself is going to be very similar to what you find in this range of scanners. When you get above this range or well below this range, you start to see different technologies. And it's important, if you're using a different scanner, that you understand its pros and cons or its strengths and weaknesses. Different scanners can do a good job with shiny black parts, for example, but in most cases, anybody that's out there looking at getting a 3D scanner, you're probably going to run into the same things that we're going to run into in this video. With all that out of the way, let's talk about parts and surface finish. So all these parts came off of one of my KTMs. This bike in particular is a 2012 250 XC, but these parts are pretty common across all KTMs. Specifically, the CNC machined triple clamp and bar mounts were common across the XC, XCF line, the SXF line. They all use the same parts. We're going to talk about specifically whether or not we even need to scan these parts later in this video. But right now, all these parts came off the same bike. These were just spares that I had laying around. And I thought it made a good comparison to look at the different surface finishes. So the first part is the triple clamp. Now this is the upper triple clamp, CNC machined, black anodized finish. We can still see some of the machining marks on here. You probably can't in video, but the main thing that we want to focus on is that this is a purely mechanical part that has a lot of interesting finishes on it, chamfers and recesses and obviously threads and things like that. But the sort of killer of this part is its surface finish, the shiny black aluminum. Now, I do have another part that's similar to this that's anodized orange. Would do a little bit better, but overall still going to have a very similar problem. So we're going to scan this part first because it's kind of our worst case scenario. So the next part that we have here is the brake lever from the same bike. Now, I didn't do any clean or prep on this part. This is exactly how I keep it in my toolbox when I go riding, just a spare that I keep with me. Now, this part is cast aluminum, and because of that, it doesn't quite have the same surface finish as a CNC machined part. And that is actually working in our favor. So this part should scan pretty well. As I mentioned, I didn't clean it, so there's still grease on the pivot, but we're gonna try to pick up some details on this and see how it does with the scan. The last two parts that I have are actually the same part. These are the bar clamps that go on the top of the triple clamp. And they are both CNC machined aluminum. They have a clear anodized finish by default. And this one, I just did a gray primer on top of. I didn't do a very good job of this, and it was pretty cold out, so there's a little bit of a texture on one side of it, which will come up in the scan, and we'll be able to see that a little bit more than you see here. But what we're gonna do is we're gonna take a look at how the clear anodized finish on the aluminum does versus the spray painted one. Now, I do not suggest that you spray paint your parts. If you happen to be scanning, let's say bodywork, that's gonna be painted, definitely scan it when it's in primer. That'll give you the best result. I don't suggest that you just primer all your parts. The reason that I did it here is because I didn't want to use the scanning prep spray. You can use things like weld inspection spray, but what happens is that's a powder. Comes out of an aerosol can, has an acetone carrier usually, and the acetone off gases after the spray gets on your part. And what that means is if you touch it or put your finger on it, you're basically smearing or wiping the powder. So in order for that to work really well, we need to sort of spray them in place. And that gets pretty messy, especially when you're doing this inside and on a turntable. As I mentioned, these parts are on loan to me, or the scanner and the turntable. I certainly don't want to send it back in that condition covered in this powder. So I ended up spray painting this because I can soak this and get the paint back off if I need to. And again, these are just spare parts that I keep laying around in case I need them for some reason. If I ever needed a triple clamp, then the bike is probably wadded up pretty bad. But yeah, so these parts I was happy to spray paint just to get a good idea. But the important thing here is we're going to talk about these different surface finishes because these are common across the board. If you're trying to do things like scan a black painted or anodized part, or you're looking at cast parts like a transmission or an engine case or a cylinder head. And we're going to kind of see how the scanner treats those and deals with those. With all that out of the way, now let's talk about setting up the scanner. Now, as I mentioned, this is an Einscan Pro HD. There are various versions of this scanner that have different pros and cons, different resolution, different amount of points that it can gather. And some of that comes down to the settings in the software. Some of it comes down to just the hardware in the scanner itself. For what we're doing here, the range of scanner isn't really going to matter that much. If you are looking at doing something like a scan to 3D print directly, if you're looking at doing something like that, say you make sculptures or you make handmade figurines or something like that, that kind of workflow will allow you to scan a part, get a mesh out of Xscan, and take it directly to 3D print. I've actually done that with this setup, and it worked pretty well. I took it directly from the STL in here, directly to a 3D print slicer, printed it here on this Ender 7, and got good results. When you're talking about mechanical parts, it's not quite the same case. We're gonna get into that later in the video, talk about the process of reverse engineering, and we'll probably do one of these parts in a future video as well. So the process of starting everything up, we need to make sure that there's power applied to the turntable and that it is hooked up to the USB in the computer. And the cable for the scanner itself has a power plug partway down. And this cable is actually pretty heavy. It's not very long. I wish it was a little bit longer for doing handheld scans. But the main thing that I want to focus on here is just the weight that this puts on the USB in the computer. Now, when I was scanning in the garage, when I was doing the car series, I actually put something underneath this to kind of take some of the weight off of it. And I think that's important, not because I'm worried about the cable. The strain relief on the cable is pretty stout, but this is going to be putting a lot of weight on the USB in your laptop or your desktop. So if you've got this thing plugged into the back or the front of your desktop and it's hanging down, I would probably just tape or do something with the cable at the desk just to relieve some of that pressure. But what we're going to do here is we need to power up the scanner, and we need to let it go through its startup process. If you rush this and you start the Einscan software, it's likely not going to connect directly to the scanner. So we do need to make sure it goes through. It starts up, it flashes a red light on the, in this case on the turntable. We're going to let it go through that process, and then we're going to plug it in. And once we have it all plugged in, then we can fire up Einscan. As we launch Einscan, the first part of this process is connecting to the scan server. So if you plugged it in and fired up Einscan too quickly, you'll probably get a prompt that says, could not connect to the device. This means that you should probably close Einscan and repower up the scanner. You can repower it up and try to reconnect inside of Einscan, but I found it's often easier just to close down the software, power up the scanner, let it sit for 30 seconds, and then try it again. So when we get started, there are 3 different options for us: a fixed scan, a handheld HD, and a handheld rapid. We did the handheld HD and rapid in their own videos of the car fender. I talked about the different accuracies there, the density of the mesh, or really the point cloud, the points that we get that get converted to a mesh, and the differences between the way that those two work. In our case, we're going to be using a fixed scan. And then we either need to start a new project or open an existing project. Now, if you open an existing project, what you're going to find is any scan data that was in that project will also be opened. So if you did capture some data, you can see here I've got some mess of a triple clamp here. If you were able to capture some data, then that's going to be contained in that project file. Generally, it's a good idea to start a new project file, but if you happen to scan something, you go about your way and you want to come back and create some new scans and align them, you can always reopen an old project file. In this case, what I'm going to do is select everything in here, delete it, and then we're going to be essentially starting from scratch. So it's the same thing as starting a new project. I just had a little bit of data there that I wanted to clear out. The first part that we're going to scan is this triple clamp, and that's because this is our worst case scenario. This is not going to work. And I already know that it's not going to work, and we just saw the results of it on the screen there. But we still want to try anyway so we can kind of understand the process. So first thing to note here is generally our brightness settings are going to be set to a point where we start to get a little bit of red in the lighter areas of our parts. In this case, because the part is all shiny black, we don't really have that, which means it's going to be hard for us to get the brightness setting just right. There is an HDR option, and with this software, the HDR option will actually give you over and under exposed scans and put them together. So that is a good option if you have parts that are tricky or parts that maybe contain multiple different surfaces, like a gray and a black surface or a white and a black surface. Using the HDR option might be a good way to get clean data. For us, I'm going to set the brightness right about where I start to see red on that shiny spot. But this is where part of the problem comes in. That shiny spot is actually a reflection from the light. It's not based on the surface finish. So what's going to end up happening is we're going to see that the laser or the scanning process is going to be bouncing around rather than absorbing that and being able to be properly measured. We are going to be using a turntable. We need to be using a feature method because there are no markers on this. Markers are not a fix for surface quality issues. Markers are really there just to align multiple scans. So we can't use markers, and the coded targets that are on the turntable are partially obscured, so it's not going to work anyways. So our only option is features, and I'm going to reduce this down to 8 steps. Essentially what we're going to be doing here with this, each step will be its own scan. Because it's on a turntable, it does a pretty good job of aligning those together, so all of those 8 scans will come together without having to do any extra work. So with those set, let's go ahead and start the scan. It's going to do a verification small move, and then it's going to start collecting data for each of those 8 positions. Now this process, depending on how many steps you have, can take a little bit of time. It's a good time for us to talk about the accuracy and the resolution. So in a fixed scan, we're getting 0.04 millimeter accuracy. That means that basically plus or minus the distance away from the scanner is 0.04. Now that is assuming that we've got an ideal scenario. If we've got a good clean part with perfect surface finish that's great for the scanner, then we can expect to see that resolution. With a part that has shininess or reflective issues, we're not going to be able to see that. We're going to get a much bigger or wider range. So keep in mind that those numbers that you see, those are ideal. And if you have a perfectly prepped part and everything is perfect, then yes, you might see those numbers. The other thing to note is that we don't have any control over the point distance when we're doing a fixed scan. It's all going to be 0.24 millimeters between points in our point cloud. If we zoom in on this, that distance between each of these points, that's going to be 0.24 millimeters, and we get this nice consistent grid pattern. But you'll notice with this part, we're picking up some areas, and I'll actually show this on the camera, the areas where we basically have aluminum or the anodized finish worn away. This is where the number plate screws on. So a lot of vibration there, and that sort of wore away the material. We get some scan information there. Inside of the threaded holes, there's still a little bit of dirt in there. So instead of the reflections bouncing around, we're actually picking up some of that thread data. We're only getting it from the direction of the scan. So as soon as it rotates around and that's obscured, we're not going to be picking anything up. So the areas where we see scan data coming through are really in corners where we've got a little bit of dirt that wasn't perfectly cleaned out, and inside of the threads that again had a little bit of dirt in them. Now these front threads, at least when I have the bike set up, I run the handlebars pretty far forward. So these front holes had bolts in them, and the back holes just end up getting dirt in them. So you can kind of see the back holes gave us more points than the front holes did because the front holes were just a bit cleaner. So this, again, worst case scenario, we're not really getting anything useful out of this. Even though I did try to clean this and I soaked it for quite a while, if we scan the backside, these pockets where this dirt is, we would end up seeing better results from the backside. But again, we're not using this because we don't really have much data from it. So we're going to select it all. We're going to delete it. We're going to say OK, and we're going to move on to the brake lever. So as I mentioned, the brake lever, cast aluminum, more of a dull finish. It is, kind of shiny, but overall, compared to a machined part, this is much more dull. I'm going to be scanning just one side of this, and I want to focus on the details. So this has a couple of casting marks on it, and it also has a detent in here and features for how it connects to the master cylinder. Again, I didn't do any prep or cleaning on this. Once again, this part is unfortunately covering up the coded targets, so we're not able to use target alignment on the turntable. If I were to maybe space it off up in the air, then we could get access to those coded targets. Because I'm not going to be using this scan either, I'm not going to spend a lot of time with it. So I'm going to use all the same settings, feature alignment, 8, and again, adjust the brightness until you just barely see that red, and then we're going to play through. Because we selected and deleted all of the scan data from the triple clamp, we don't have to worry about overwriting anything. If we were to just start a new scan without deleting any of that, then we would have a second set of 8 scans. And that's perfectly fine. That's what we're going to do for our final part. But you can already see a big difference in the quality here. We're getting a lot of points on the screen, and we're getting the definition of the lever, and it looks 1,000 times better than the triple clamp did. So again, cast aluminum part is a little bit more dull. This is something that you would see on things like transmissions and bell housings, engine blocks, cylinder heads. These are all the types of parts that scan really well with limited prep work. Now, I say limited, you still want to clean them off. You want to get grease and grime and stuff like that off. But overall, this looks pretty good. Now, one thing that we will notice with this is we can kind of see areas where maybe there was more reflection are not coming in as well as the areas that were a little bit more dull. So you can see the casting marks look pretty good. Details about the pivot point, how it attaches to the master cylinder, the little recess for the spring. All of that looks really good, and this is probably enough data for me to reverse engineer a part based on this. Now, if I were scanning this, which we will talk about later, we'd have to think about what we're going to be using the scan data for. We're not keeping this, so again, I'm going to select it all and delete it, and we're going to move on to our last two parts. So the next part is going to be the bar mount, and again, this is anodized aluminum. It's clear anodized, and the aluminum underneath, there's still some CNC toolpath marks, but these parts generally are going to be either sandblasted or tumbled to give this dull finish. And even though it is shiny when you hold it in certain light, this is a much different beast than the triple clamp. So we're going to take a look at this. And thankfully, this part is small enough that it fits inside the center of the turntable, so we can use the coded targets here. It says don't block the coded targets, it's perfectly fine. Make sure that we do adjust the brightness, again, just so we barely see that red on the edge. And for this one, I'm gonna do 8 again. There's no reason to do 16. For the final part, we will do 16 scans, but just for this one as a test to see what we get, we're gonna just do 8. Now, one thing that happens with parts like this that are sort of just on the edge of being okay to scan, you'll notice that the angle of the scanner relative to the part will make a big difference. If you have areas on your design that are perpendicular, so this face here, if that's perpendicular to the scanner, then we're going to get a pretty good result of that face. However, anything that has a slight angle, the reflections coming off of that will oftentimes be difficult for us to capture. So let's take a look at the results. We can see that we do have some remnants floating around in space. And again, if we rotate this around, let's go ahead and just see if we can get a clear view of it. You can see here that right around that fillet, we're getting these points out in space. We see it here again, and that's right there on that fillet. And part of the reason for that, part of the reason we're seeing that, is if you think about a shiny part, if you think about rendering it or taking pictures of it, then you have this effect of caustics and bloom with shiny parts. Now, the bloom is going to be sort of this halo that we see based on how light bounces off the part, how shiny they are. That bloom effect is what we see when we're scanning as well. And the way that the light hits these fillets and these corners, you'll notice that when you come up to a filleted corner, a lot of times with these parts, you might end up seeing points out in space. And again, it's because it's distorting the data, the feedback that's coming back to the scanner. So we're not using this one. Let's go ahead, select it all, delete it, and let's move on to the final part. So for the final part, I'm going to do 16 steps. I also want to adjust my brightness because now we're dealing with a flat part. I need to increase the brightness a little bit. But once again, we're looking to get just a little bit of red, and then we'll allow it to start scanning. Once again, it is small enough that it fits, and we can use the coded targets. One big thing you'll notice using coded targets as opposed to feature alignment is the plane where all the coded targets are is automatically removed for us. We don't have to do any extra work. All right, so here we have all of our 16 scans, and this looks much better than anything else we've seen. So in the corners, we can still see a few points floating out in space, but overall, this looks really good compared to anything else that we've scanned so far. I'm not going to do any cleanup or removal of anything because, as I mentioned, when you're using the coded targets on the turntable, they're automatically removed for us, so we don't have to do any extra work. So next, we're going to flip it over. So that way we can capture the rest of the data. I'm going to use all the same settings and just hit Start Scan. Because we didn't delete that first set of 16 scans, all of that is still saved in the system. It's automatically going to create a new set of 16 scans. And because we are using coded targets on the turntable and it does have sort of a hybrid feature alignment, it'll automatically put them together for us. Now, this is not a perfect approach because some parts will be a little bit harder than others. These parts, having so many unique features, gives it a great opportunity to align them for us without us having to do anything. You do still have the option to go through the manual alignment process where we can pick at least 3 points and we can use those. For a part like this, you would want to make sure you pick points that you can use to define planes. And because we're flipping this over, one scan won't have points on the top and the other scan won't have points on the bottom. So you really will end up using things like these flat sides here and somewhere along the rounded faces. So it's much better to just let the software do it in this case. But some cases, again, you might find that that doesn't work that way. So once again, just like we would expect, the scan data looks pretty good. As we zoom back, we see it looks like there's some bumps here, and that's from the spray paint. Now, as I mentioned, I did this in the cold. I did it relatively quick. So that's an area where the paint actually dried before it hit the surface. And it's hard to see on the actual part, but you can pick it up in the scan. So again, that goes down to that resolution and the accuracy. That 0.24 millimeters between points and the accuracy of plus or minus 0.04 gives us enough detail to where we can kind of see the paint that flashed or dried before it hit the part. Everything looks good here. We're going to say okay. It's going to process this with the previous 16 scans. And then what we're going to see is it does a pretty good job of aligning things. Now, one part of the process that's different here versus doing our handheld HD scan is we need to do a global optimization of these scans, and then we can convert it to a mesh. We do have the option to go in and manually do some alignment. We can also save our scan, which is an ASC file. If you happen to be using targets, then you can also save the target data. I did mention in previous videos that ASC file can be opened by some programs like MeshLab can open that, but other programs like Geomagic and even Xscan can't reopen that data. It's essentially the raw point cloud dump, and the P3 is the raw dump of the markers. So if you want to save that as sort of an extra backup, then you can certainly do it. For us, we're going to do a global optimization. And once again, what it's doing is it's going through, keeping in mind that we have 2 sets of 16 scans. It's trying to optimize the points in those areas. And what you're going to find out is that we're going to have a lot of point density in some areas because we've got 2 sets of scans. And then other areas, like the top and the bottom, we've only got 1 set. So the point spread is going to be a little bit different. And that point spread is used when we convert this to a mesh. Once we've done that optimization, now we have the option to mesh the model. Now, meshing the model takes it from all of these points that we have, this point cloud, and then it applies triangular faces between all of them. Now, we have a couple of options here, and this is a good time for us to talk about what some of these options do and why we're not going to use them. So as we look at this, the counter bore where socket head cap screw fits in to bolt this thing down to the triple clamp, that wasn't captured, and mainly because I didn't paint anything inside of that area. I only painted the outside. So that data didn't really come in the scan very well. You can kind of see these triangles here, and that's because of the different angles where we scanned it. We rotated it 16 times, and it was able to get a little bit more in there each time. But the reason that we don't want to do things like make this watertight is it's going to fill in information that's not there, and we don't really want to do that. We don't want to destroy the raw scan data. The other thing that we don't want to do at this stage is we don't want to smooth it, because what's going to happen is it's going to start averaging the location of these points when it's trying to convert it to a mesh. And that's something that we can do downstream if we decide to remesh and try to preserve sharp corners. That can happen after the fact, but once we change it here, we can't go back. So my general process here is to keep the raw data as raw as possible. It's very easy to go in and start smoothing things out. And if you're doing something like a hand sculpture that's going direct to 3D print, you can smooth it out in here just fine. And if the result is okay for you, that's fine. But with mechanical parts that we want to reverse engineer, we don't want it to start averaging point locations, because then we start losing detail. So the max triangles, this is actually quite a bit higher than the number of triangles we captured. I'm not going to limit it here. When you're getting your scan data, it actually shows you the triangles in the bottom right corner, so you'll be able to kind of get a feel for how many you're pulling in. even though it's capturing points and not triangles at that stage. The reason that you would want to limit the max triangles is because Fusion specifically, as well as other CAD software, the higher number of triangles, the harder time it has capturing that and working with that data. So partially it's based on your computer specs, but there is an actual limit where you have too many triangles and it'll just hang up on itself. Filling small holes generally is okay, but you have to note that the small hole is 10 millimeters or less. Now, when we're talking about this part, these are essentially 10 millimeter holes for these screws. It could potentially try to fill that in. We don't want that, so we're going to turn that option off. Removing spikes, I'm actually okay with this setting because we do have a couple points that are floating out in space, and those are going to turn into spikes when it gets converted to an STL or a mesh file. So I'm going to allow it to do that, and also allow it to remove small floating parts. So that'll allow us to sort of get rid of some of these points that are out in space. Some of these other options for filtering and smoothing, again, really what we're doing is we're decimating the point cloud as we turn it into a mesh. And unless I have a good reason, I'm going to leave all of those settings off. So the benefit at this stage is we can apply it, we can preview it, and we can decide whether we want to confirm or reset those settings. So this is actually a good time to play around. We can see that we do have a couple of areas where we still have those little spikes, and we end up getting some holes in the top and the bottom. But if we're going through the process of reverse engineering this part, you need to look at what data you actually need out of this. Can we still build a plane out of the data that we have here? The answer to that is yes. Let's see. Let's go ahead and increase the remove small floating parts to 40. We're going to reset and apply and allow it to do it one more time. And we'll just kind of take a look at the results and see if we're happy with them. You have to remember that at this stage, it is doing something to the point cloud, and it is going to eventually reduce some of the raw data that we got. But you have to look at whether or not that's going to be an okay solution. You can see we got some divots and some spikes here. We've got some over here. But really what I'm looking for is, do I have enough mesh in this area and this area to define a plane, for example? It looks like I do. It looks like I have enough to figure out where some of these transitions go and enough to create this outside shape. So I'm happy with those results, and it can be very hard to say confirm at this stage when you see a mesh that looks like this. But again, it's all about gathering that raw data and then processing it downstream rather than worrying about processing it now. There are options at this stage which are destructive. So if you delete any of this mesh, it's gone. But we can do things like manual hole filling. Now, when you do this, note that a lot of these holes are right around the edge of the part, which means that if we select them, we are going to be affecting the edge of that hole. Now, the reason that this is important is because downstream, if we were to reverse engineer this in Fusion, we would be doing a mesh section sketch a little bit further down from this edge, but this is affecting the edge. This is going to be problematic for that edge. We can try to do this as a flat and see if that has any better effect, but you'll notice that flat is messing up that corner as well. So this is again an area where you need to say, is the data that we have here enough for my purposes, or do I need to somehow clean and process all of that? I, again, am of the mindset that for a part like this, a mechanical part where the intent is to reverse engineer it, leave the data as raw as possible and then process it downstream if you want. Because we can take this raw data, we can copy it and we can smooth it out, and then we can look at the difference between the two. So at this stage, I'm happy with it. Which brings us to the last part of this process, and that's moving into what's called measurement. Now this is a little misleading, but what we're doing in measurement is we're creating a plane, a line, and a point. Now the plane, line, and point are going to be used to define our coordinate system. If we look right now and we rotate this, the coordinate system is based on the orientation of the scanner relative to the turntable That's not what you want to take into CAD to try to reverse engineer this thing. So we need to start to define where we want these different planes and lines and points. And the way we do that is with creating features. We're going to do this first by creating a plane. I'm going to select 3 points, and I'm going to select 3 points that I feel are an accurate representation of the base. We're going to create that. If we want to do this again, for example, if we want a plane off the bottom of this part, we create another plane, that's plane 2. We can rotate this around. We can create another one off the side of the part. We'll create that as plane 3. If we want, we can create one off the top of the part. Again, finding good references. That's plane 4. Over here, you can see the spray paint or the overspray was pretty bad. So this is not a great place to try to capture a plane, but that's okay because we don't necessarily need it. Now, if we move on to a line, the plane is going to define normal z when we set up our coordinate system. The line is generally going to define the x direction or the y direction. What we're going to do is we can either select 2 points, which is going to be just visually picking points on the mesh to define a line, or we can use a plane-plane intersection. Now, plane 3 on this sidewall is going to come down and intersect with plane 1 or plane 2. And when we do that, we're able to create a line that we can then use as either x or y. We can see it applied to that edge, and it actually tracks the edge really well. So that's the best option for us, as opposed to manually picking points that may or may not really give us anything useful. And then to define a point, we have either a line-plane intersection or we have a selected point. Now, this is where this process kind of falls apart a little bit, because for reverse engineering this thing, I would love that point to be in the middle of that circle. I don't have an option to do that. I have to select something on the mesh. So we either need to manually pick a point somewhere that will represent our origin or XYZ 0, or we need a plane that is going to essentially give us a definition of, where that plane and that line intersect. I don't really have a good plane line intersection. So what I'm going to do is I'm going to manually pick a point that I feel is roughly centered on that hole, just close to the edge, and that's going to be my XYZ 0. I can manually move the mesh when I get it into CAD. Not as precise as you would like it to be, but we don't really have a great option for putting that point at 0. So now that we have our planes, our lines, and our points, we go to the Movement tab, and this is going to allow us to use the 3-2-1 system. So again, a constraint plane, plane 1 is going to define z plus. Now we can also have it define y if we want to. And then we have a line, which is going to define our x direction. And then we have our constrained point, which is going to be where XYZ 0 is located. Once we say move, now when we take a look at this, we can see that the part is oriented based on XYZ. We have our view cube in the bottom. We can rotate this thing around, keeping in mind that the view is perspective. It's not orthographic. So as we move around and we take a look at this, as you move left to right, you can kind of see the perspective. So you have to keep that in mind, that as we're looking in here, we are looking at it in a perspective view. There are settings in the software here, but I haven't found any that will actually allow you to toggle it from perspective and ortho. If that is in there and somebody knows, please leave a comment. But basically what we're doing is we're setting up XYZ 0 and we're moving the part to that. At this stage, now we've got the points captured from our scan. We did any minimal processing that we wanted to do. So now we converted it to a mesh. We then took that mesh and we brought it in and created our plane, our line, and our point for our 3-2-1 alignment system. And then we moved it into that coordinate system based on those selected planes and points. At this stage, what we want to do is we want to save this out as a scan now. We want to save it as our mesh. So we're going to click Save Your Scan. We are going to pick our project, so motorcycle parts, and I'm going to save this as an OBJ, an STL, and a 3MF. Simply just because I like the redundancy of having those three. If you were doing things like a textured scan, you would want to use 3MF because it does bring in appearance data. The STL is not going to do that, but for us, again, it's just kind of a redundancy thing. So I'm going to do 250 XC bar clamp, and now I have saved out that scan data. Now I know this took a little bit to go through the entire process because we were looking at all the different pieces and through the entire process. In reality, start to finish, assuming everything was set up and the part was already painted or prepped, I would take about 5 to 10 minutes. I mean, it really isn't that long for us to get a mesh of this part once we start scanning it. So I did 16 scans. You could do more, you could do less based on the part you're scanning, but the process doesn't really take that long. I didn't speed up anything in terms of how long it took to scan. It's just all kind of there. So yeah, I think you could get this in about 10 minutes. But now that we have this, the next part of this is to talk about whether or not we had to do it. So that's kind of the tricky topic with 3D scanning is when would you 3D scan something and why would you 3D scan something? There is a common misconception that you can come in and 3D scan something and just have a perfect 3D model of it. And unfortunately, that's just not the case. There is still a bit of human interaction that has to happen before and after the scan process. So as we saw with the triple clamp, we got next to nothing out of this. So in order for me to scan this properly, I would need to go through and really clean it, get rid of all of dirt and residue, and I would need to prep it using a scanning spray or maybe make it a sacrificial part and spray paint it, knowing that I could use paint thinner or something and get that back off. So in order to do that, I would need to spend a lot of time prepping this part, probably several hours. And at the end of the day, is it worth it? No, it's not. Not for this part, it's not. And the reason for that is because I don't really have any reason to reverse engineer this part. If I needed this data, I would be designing a new triple clamp. So all I really need to know off of this part would be some basics that I could measure. I know because of the size of the forks, what size these are. I know because KTM publishes it that this is 22 millimeter offset between the center line of the stem and the center line of the forks. I would likely change where the bar mounts are and how they interact, so having information about that isn't really critical to me. So really all I need to know is the size of the forks, which I know, the offset, which I know. I would need to measure the stem data about how it sits on the bearing and thrust washer and all that stuff. And the way that KTMs do it, Japanese bikes have jam nuts underneath that will actually preload the bearing. The way that KTM does it is actually with this. So anybody that's out there working on a KTM, if you unclamp your top triple clamp, your forks are going to fall. I unfortunately learned that the hard way the first time. But yeah, so I would just need to measure and gather some information about how tall this is in relation to the stem that's being used. So that all can be measured. And there's really not a great reason that I would need to scan this part. With the brake lever, however, this part is not really prismatic. This is much harder to measure. There's a lot of sort of curvature to this part. And even if I was making a CNC machined version of a brake lever, which I have on my Supermoto setup, I would still probably want to scan this. And the reason I would want to scan this is because the location of the pivot point in relation to where your fingers are on this, all that data was done through hours and hours of testing and research and so on, and the shape of it and everything. So that is important to me. So getting that critical data into the computer would be important to me. Information about the pivot point and its relation to how it attaches to the master cylinder. Again, that is all stuff that would be really hard to measure. It could be done, but it's much easier to scan this and have a digital reference of it, and then I can build from there. Now, if you don't have a 3D scanner and you wanted to still get that out of your parts, the way that I have done this in the past is put this on a piece of graph paper and trace the critical details. So for example, the detent where the spring goes, I don't necessarily have a good way to capture that in a 2D view like this, but you can put a little bit of a line there that indicates where that feature is. That way you have a piece of graph paper that has a known scale on it, and you can capture some of the critical detail. But if I had the scanner, if I had it set up, there's no reason I wouldn't scan this and bring this into the computer. The bar mount is kind of an in-between. The critical details of this can be measured fairly easily. The size of the counterbore in the center, its location in relation to the clamp portion of it. So the critical details can be measured. The cosmetic details about the shape and the transitions for the ball end reliefs and things like that, those are much harder to measure. So if the goal is to replicate or recreate a part that's similar to this, maybe with some different offsets or dimensions, then I would scan this part as well. And that's simply because it's hard to capture that data by measuring it. Now, you could also make the case that you could just visually eyeball it because it's probably not a critical detail to its structure. But again, if I had it set up, there's no reason I wouldn't scan this and have it as a reference in the computer. If the triple clamp was prepped, then there's no reason I wouldn't scan it to have as a reference as well, but you don't necessarily have to, is the point of that. So at the end of the day, for me, fixed scan, turntable, it's a great option to have if you are doing scanning for knickknacks, things that you make by hand, sculptures that are sort of one-offs and not really a mechanical or prismatic part. This is a great option to get a digital version of that very easily. If you're reverse engineering mechanical parts, the chance of you having parts that perfectly fit in the sort of envelope of the turntable and them having the correct surface finish is probably a little bit less than with a sculpture or something like that. But if you do parts like this all the time, if you need to reverse engineer them or recreate small car parts or motorcycle parts or whatever the case might be, it could be a great option for you to have. I think the big benefit for a scanner like this, or scanners in general, are for scanning bigger items, things that are hard to measure, things that are more cosmetic in nature, not necessarily prismatic. So car fenders, for example, if you need to make a wide body or recreate a fender, measuring the curvature on something that exists is extremely difficult and would be next to impossible to get accurate data out without something like a 3D scanner. So that is a very good option. Scanning a part that you need to build something to fit. So scanning a cell phone, for example, or scanning some sort of thing that you need to make a cradle or a feature that attaches to it. That's another great option for a scanner is to capture the details or the data from something you don't have digitally that you need to build around. So those are great options for the scanner. Mechanical parts, if you can measure it easily, you can go either way. Parts that have more curvature, scanner is definitely going to be a big benefit there. Overall, the process is relatively simple. It's easy to go through with Einscan, just a couple steps in the process. The only place where I think there could be a couple of improvements here is that currently, at least on my system, it's not really touching the GPU. It could run a bit faster with heavy scan data if it was able to tap into the GPU a bit more. Maybe it's just my laptop and the way it's set up. Maybe other people have that same sort of experience with it. For these parts, it ran relatively quick. Like I said, 10 minutes you could be done for a part like this. The other thing is I would love for the movement, the XYZ position, to be able to put that point at the center of a hole. If there was a way to select points on a hole, let's say 3 points, and apply a circle or cylinder and then put a point at the center of that, that would be perfect to take this into CAD and reverse engineer. It's not there right now, or if it is, I don't know how to do it. But overall, process super simple, very easy. If you have any questions on this or anything else, please let me know. As always, thanks for watching, and we'll see you in the next one.